Hi. So let's remember what we're talking about here, right? What's reality? Reality is that there's something in this world called charge. And we have observed, hopefully in lab you have seen yourself and you've seen me demonstrate that like charges repel. There's a force on like charges. They repel, they want to go apart from each other. And opposite charges attract. These really want to come together. Right. That's reality. We're just trying to wrap our brain around it, right? So really this whole last chapter and a half, 20 and 21, has just been trying to wrap our brain around that phenomenon. And it's all different aspects of it and trying to visualize it in different ways and different levels of abstraction. So what I want to do in this video here is to connect the visualization of this that we're calling the electric field with the idea of potential. Now, electric potential and electric field are not really two different entities, right? They're not totally different. They're two distinct ways, two different ways of representing one situation, right? And so to kind of review a little bit, we started off with the Coulomb's law model of force, where charge A directly affects charge B. And we don't really care how that happens, we just know that it does. There's a force, right? And we use Coulomb's law to describe that. Now, the next representation we did is we said, hey, okay, charge A actually creates an electric field which permeates space around it. Charge B now interacts with that field and experiences a force. Okay, that's nice because it takes away this action at a distance, right? How do these two charges know that the other one is there? So that's why it's nice. It's a little bit tricky because it's a vector, and as we've seen, vector problems can be pretty tricky. It turns out that the potential is the same thing, right? It's just another way of visualizing this interaction, right? We could visualize it as this charge creates a potential which fills space around it, and then this charge interacts with that potential. Now, why might we do that instead of the electric field? Well, mathematically, potential is just easier because potential is not a vector. And potential is so closely related to potential energy that it's also a very important idea. So the point of this lecture is to convince you that these two ideas are two faces of the same coin. One way to represent this is using what we call lines of equipotential. But as I've done throughout this whole chapter, we're going to build up an analogy with gravity and height, where where potential is like our height in an electrical landscape. So here we see a picture of this mountain in Glacier National Park. And we can see that it's got a real steep side over here, maybe not quite as steep over here. And here we see a topographical map of the same mountain. Now, looking at this topographical map, how can you tell whether the mountain is steep or not? Well, if you've ever read a topographical map, you know that each one of these lines is a line of equal elevation. So if I was to walk along one of these lines, I would be staying at a certain elevation, and that would not be changing if I was walking along these lines. So notice these potential lines, these equal elevation lines are separated by 100 feet. So here's our 2,000 foot elevation line, and everywhere along here is at 2,000 feet. So how can we tell which side is steeper? Well, if I move from one line to the next, I have changed my height by 100 feet. If I do so right here, notice I travel quite a long ways to go up 100 feet. However, if I was to do that at a different place on this map, say right here, well, look how far I travel here to travel 100 feet, or where this arrow is. How far do I travel here to go 100 feet? A much smaller distance. So clearly it is a much steeper mountain right here than it is right here. Okay, so notice that we can look at this flat representation, and honestly, all of the information is contained about the shape of the mountain, right? So in this flat representation with lines of equal height, everywhere We can visualize the shape of the mountain with enough practice without seeing this picture. We can even tell where it is steeper and where it is not as steep. So we can use this idea of lines of equal elevation in an electrical world also. And so here is something very similar. In the electrical world, we're going to call this a contour map. This is called a contour map. And it represents these lines of equal potential. Recall that potential is like our height in our electrical landscape. So everywhere along this line right here is 20 volts. Everywhere along this line is 40 volts. So here's a little electrical world, and it looks like we have 2 positive charges and 1 negative charge here. How can I tell? Well, in our electrical landscape, positive charges make mountains and negative charges make valleys. So we could represent this as this sort of 3-dimensional elevation graph, or as a contour plot, or if we were to draw some lines straight through here, right about here maybe, across here on the x-axis, then we would see the potential varying across as we went. Okay, so this is a couple of ways to represent the potential. Looking back at our topographical map, notice that we can tell how steep this is by how close together the lines are. I already stated that. Also notice that the steepest part of the mountain, the steepest downhill descent at any point on the mountain is always perpendicular to a contour map, to a line of equal elevation. In other words, if I was walking along this 2,000-foot line, then I would neither be going up nor down. If I was to move perpendicularly to that, that is the very steepest ascent that can be had at that point. If you are familiar with the term, skiers or mountain climbers talk about the fall line, right? If I'm on a mountain, then it's downhill all over here, right? But there's only one direction where it's the absolute steepest, and that would be, maybe it's here. That's what we call the fall line. And similarly, in a contour plot, that fall line, the direction of steepest descent or ascent, will always be perpendicular to a line of equal elevation. Same thing here. The potential will always change the greatest if I'm perpendicular to a line of constant potential, and it changes not at all if I move along a line of constant potential. What this means is that the electric field is always perpendicular to a line of equal potential, and the electric field always points in the direction of decreasing potential. Okay, so again, electric field is always perpendicular to lines of equal potential, and it always points downhill or towards lower potential. And so, if we're to think about these equipotential lines, right? If I moved a charge along this equipotential line, its potential is not changing. Therefore, its potential energy is not changing. The line of steepest ascent or descent will always be perpendicular to that. In other words, if I moved the charge perpendicular to my line of equal potential, then that would change its potential energy the greatest. We always say that the electric field points from high potential to low, or downhill. Let's do a quick example. Rank in order from largest to smallest the electric potentials at the lettered points of the electric field shown. So these lines here represent an electric field, and I want to know where is the electric potential the highest. Why don't you pause the video, and I will see you on the other side. Okay, welcome back. Recall that the electric field always points from high potential to low potential, always from high to low. So that means that A is the very highest potential, B next, C next, and D next. Notice that there would be a line, I haven't drawn it here, but there is a line of equal potential everywhere here where we are perpendicular to the electric field. So the potential is the same everywhere along some line right here, perpendicular to that electric field. Everywhere along some line here, the potential is the same. Everywhere along some line right here, the potential is the same. And everywhere along here, the potential is also the same, giving us this ranking here. Here are a couple of situations that we've talked about. Here is a point charge. The electric field due to a point charge points straight away from it. Everywhere, the field lines are perpendicular to the equipotential lines. These equipotential lines, notice the spacing gets greater as they go farther out. More on that in the next lecture. Notice that the electric field always points from high potential to low potential, which means that the very highest potential is here in the center and that it goes down as you get farther away. What else could we learn here? Well, recall that the spacing of the electric field lines is proportional to the magnitude. So we see that the electric field is stronger here than it is here. Here's our dipole. Same thing. Electric field lines point from positive to negative. Equipotential lines are always perpendicular to electric field lines. The positive is the high potential. The negative is the low potential. Electric field lines always point from high potential to low. They always point downhill. Here's our parallel plate capacitor. We see a similar shape for any scenario that creates a uniform electric field. That's easily done within a parallel plate capacitor. The electric field points from high to low, from positives to negatives. This is the high potential side of my capacitor. This is the low potential side of my capacitor. In a uniform electric field, the equipotential surfaces and lines are perpendicular to the electric field lines. We've already said these first four things. Four important properties about conductors in electrostatic equilibrium. We said this in the last chapter. Excess charge resides on the surface. That's because that's the farthest all of that charge can get away from itself, from each other. The electric field inside is zero. Recall that a conductor is something where charges can freely move. If there was an electric field in the conductor, those charges would just experience a force and they would move until there was no longer an electric field. 3, the exterior electric field is perpendicular to the surface. Again, those charges would move until it was. In number 4, the field strength is largest at sharp corners. Now we can add a fifth important property about conductors, and that is that the entire conductor is at the same potential. And thus the surface is an equipotential surface. Now, it's important, I think, to add this to the list, but notice that we could have deduced that because we know that the electric field inside a conductor is zero. And an electric field points straight downhill. It points from high potential to low potential. If there is no electric field, then there is no change in potential. So, point 5 and point 2 are really the same thing if we're convinced that electric field and potential are two sides of the same coin. And hopefully you are. So inside a conductor, the electric field is zero, as I was just saying. Therefore, you can't do any work on a charge moving it. And therefore, the potential change is always zero within a conductor.